Hello friends, welcome to the today's lecture. In previous class, if you remember, we have discussed this kind of functional. Let us say call it g of y of x is equal to say x0 to x1 f of x y y dash d of x such that y of x0 is equal to y1 and y of x1 equal to y of x0 equal to y0 and y of x1 is equal to y of 1. And we have discussed the Euler equation, which gives the necessary condition that the curve y is an extremum for this functional j y, and it is coming out to be that Euler's equation for this is reduced to your f of y minus d by dx of f of y dash is equal to 0. So basically it is a second order differential equation in terms of y, and so this equation represent the solution of this equation represent the curve which extremizes the given functional this. Okay, so in a previous class we have derived this equation and we have discussed certain sub cases of this. In fact, we have discussed the following cases. If you look at the case 1, when function f is equal to f of xy, it means that f is independent of y dash, and in this case your Euler's equation reduced to your simple finite equation, that is derivative of f with respect to y is equal to 0, and we have seen that in general it may not have a solution, but if the finite equation which we have obtained passes through the boundary points, then it will have a infinitely many solutions, and we have seen. And in the second case, when f is a linearly dependent function on y dash, in this case also we have discussed two sub cases. One that Euler equation reduced to my equal to n of x, and if this my equal to n of x satisfy the boundary condition, that we have a extremal. Otherwise, if my is equal to n of x is identically equal to 0, then or we can say that my is equal to n of x is there, then the extremal is basically coming out to be constant, and it does not depend on any say curve y of x. So in this case, when my is equal to n of x, then this extremal has this extremal of function has no meaning, because it depends only on the end point. So in this case of 2, there are two sub cases, and we have discussed these two cases, sub cases, and examples also based on this. And in case 3, when f is depending only on y dash, here also we have seen that all the extremal lines are coming out to be straight lines only. So this also we have discussed one example also. And case 4, when f is equal to f of x y dash, that is f is dependent solely on x and y dash, and here we have seen that in this case your Euler's equation reduced to your differential equation depending on y dash, and we have discussed certain cases also. Now in this lecture we start with the case 5. So here, since f is independent of x, then this term f of x y dash is coming out to be 0, and this reduces to f of y minus y dash f y y dash minus y double dash f y dash y dash equal to 0. So here if we observe carefully, then if we multiply that after multiplying this equation, this differential equation by y dash, this becomes an exact derivative of f minus y dash f of y dash. Here we can check that if we expand this form d by dx of f minus y dash f y dash, then we can say that since f is a function of y and y dash only, then derivative of with respect to x will be f of y y dash plus f of y dash y double dash. So that is the total derivative of f with respect to x minus now we are finding out the d by dx of y dash f of y dash. Now f of y dash, and we are taking the derivative of y dash with respect to with respect to x, then it is coming out to by y double dash minus f y dash square minus f of y dash and y double dash. Now here these two terms, this and this will these two terms, this and this will cancel each other, and this reduces to this form where we can take out this y dash common, and it is nothing but this. So Euler's equation when f is independent of x is precisely the value of this quantity is equal to 0. So it means that if this quantity is equal to 0, this implies that d by dx of f minus y dash fy dash is also equal to 0. So if we solve this, if we integrate this d by dx of f minus y dash fy dash equal to 0 with respect to x, we can say that we have this equation f minus y dash f of y dash equal to c. So this is your first order differential equation in terms of y dash, and this does not contain your the variable x in explicit manner. We can solve this equation with respect to y dash, and with the usual method or with the introduction of any kind of parameter. So let us take an example based on this and see how important this case is. So the example is minimum surface of revolution problem. So here the problem is to find out the curve with fixed boundary points such that its rotation about the axis of abscissa gave rise to a surface of revolution of minimum surface area. For example, if I look at here, so we have this, I think we have already discussed this problem. Let us say that we have a curve like this. This is your point x naught, and this is the point your x1, and if we this is y of x, and here if we revolve this curve along this axis x, then you will get a surface like this, and we want to find out that under what curve this y equal to y of x, the surface area of this shape is minimum. So here a surface area of to find out the surface area, it is what we try to do, we simply take a small element, and here this is your y of this is y. So surface area is going to be your 2 pi y d of s. So you can say that here surface area between x0 to x1, you can calculate it like this: x0 to x1 2 pi y of ds, and let us call this as a functional based on y. So g of y represent the surface area of this revolved shape, and it is given by x0 to x1 2 pi y of ds. So it means that if you change your y, your surface area is going to change, and hence the value of this integral will also change. Now we want to find out, say, curve y such that this integral, or you can say this functional, is minimal. So here let us simplify this further. So here we have x0 to x1, this 2 pi y, and ds you can write it ds by dx, and d of dx here, and this ds by dx you can find out as 1 plus dy by dx whole square, and d of x, values of x is x0 to x1. Here in fact you can write it here, the point say s1 and s2, which is corresponding to the point when x is equal to x0 and x equal to x1. So we want to minimize this functional. So here if you look at, this is nothing but a functional, this is the functional independent of say x. So here your x is not present. So here this case is coming under the sub case 5, and here in this case your we have defined here I, we have discussed is like j. So here we have seen that this the surface of revolution, the area of the surface of the revolution is given by j of y of x equal to 2 pi x0 to x1 y under root 1 plus y dash square d of x. So as we have discussed here, that this Euler equation is reduced to this, that f minus y dash f of y dash is equal to c1. So here f is y under root 1 plus y dash square. So if you simplify this f is y under root 1 plus y dash square, and if you y dash, and then if you differentiate this with respect to y dash, you will get this, and after simplifying you have y upon under root 1 plus y dash square is equal to C1. So basically this is a kind of a first order differential equation. We may further simplify by squaring it on both the sides. So here we have this we can solve by squaring it and then find out a differential equation in terms of y dash, or a simpler method we can evolve by saying that if we take y dash in a way that, let us say, y dash is equal to sine of hyperbolic t. So if we take y dash as sine hyperbolic t, then 1 plus sine square hyperbolic t is basically cos square hyperbolic t. So here under root is there, so you can take that if y dash is sine hyperbolic t, then y is coming out to be C1 cos hyperbolic t. So you can write it here that let y dash equal to sine hyperbolic t, then y is coming out to be C1 cos of hyperbolic t, and we can find out say variable d of x as dy by upon y dash, and dy you can calculate dy is sine hyperbolic t, and y dash you can simply say that it is coming out to be C1 dt, and when you integrate it, it is coming out to be x is equal to C1 t plus C2. So here your curve is given in terms of parametric form, that is y equal to C1 cos hyperbolic t and x equal to C1 t plus C2. So this after removing, if you so this is a parametric representation of the curve which minimize the surface area of revolution, and we can simply find out the relation between y and x by removing the parameter t here. So you can find out the value of t here as x minus C2 divided by C1. So your equation of the extremal curve is given as y equal to C1 cos hyperbolic x minus C2 upon C1, and this curve basically represent a family of catenaries, and the shape which we obtain by the revolution of these catenaries is called catenoids. And here if you remember, here we have two constants C1 and C2 that we can obtain by satisfying the condition that y of x naught is equal to y naught and y of x1 is equal to y1. So these C1 and C2 you can obtain in terms of x naught and y naught. And please remember, here we can solve this equation y upon under root 1 plus y dash square equal to C1 by squaring and simplifying for y and y dash. So this also you can do. In fact, let us see here, this is your y upon under root 1 plus y dash square. I am just giving you a small hint how you can solve it, right. So if you square it, you have y square equal to C1 square 1 plus y dash square, right, and you can simply say that it is y dash square is equal to, you can say that it is y square minus C1 square and divided by basically C1 square. So here you can say that y dash is equal to under root y square minus C1 square 1 upon C1. So here this you can say that it is dy by under root y square minus C1 square is equal to 1 upon C1 d of x, and if you integrate on both the side, then you will get this as what is that, this is cos hyperbolic inverse y by C1 is plus some C2 is equal to say x by C1. So if you simplify, you will get the similar kind of relation you are getting, and you can simplify and you can get the value of y. Is that okay? So here this is the example based on the case 5. Now let us take one very important example of this Euler's equation, and that is the finding the curves which minimizes the distance between any 2 points on a given surface. So we can say that, and that is known as a geodesics. So geodesics, you can define it like this, that a geodesics on a surface is a curve along which the distance between 2 points of the surface is a minimum. So what it means, that you have a surface, take 2 points, and then you can join these 2 points by some curves which are lying on your surfaces only. So out of those curves on your surface, you need to choose the curves which minimizes the distance between A and B along the surface, and whatever curve you will get as a minimizer of the distance, that curve is known as geodesics. So we have seen the first example earlier also, but let me frame this example here also. So first example is that show that the geodesics on a plane are straight lines. So here your surface is your a plane. So on, if we have a planar surface and if you want to find out geodesics, then it is coming out to be straight lines. So how we can form solve this using the Euler's equation. So here we have a curve which join the point A and B, where A is denoted as x1 y1 and B as x2 y2 in the xy plane. Then you can find out the length between A and B as A to B d of s, and d of s you can write it as under root 1 plus dy by dx whole square. And so you can say that the functional s represent the length between the point A and B, whose x coordinate is given as x1 and x2. So we have to minimize this functional, right. So the geodesics on the xy plane is the curve y equal to y of x, for which this functional s is minimum. So here if you look at the integrand is what? Integrand is under root 1 plus y dash square, and which is independent of x and y, or we can say which depend only on y dash, and hence we can use our sub case and we can get the Euler equation is nothing but d by dx of del f by del y dash equal to 0. So here we can again pose this equation as del f by del y dash equal to constant, which we have discussed. But if we look at the value of del f by del y dash, it is coming out to be 2 y dash upon 2 under root 1 plus y dash square. So when you simplify this, then it is coming out to be a second order differential equation like this. But after simplifying, it is nothing but only this y double dash is equal to 0. So when you, this is a second order differential equation, very simple second order differential equation, whose solution is nothing but this c1 of c1x plus c2. So here this is nothing but only a straight line, and this c1 and c2 you can obtain by the condition that y of x1 is equal to y1 and y of x2 is equal to y2. So this c1 and c2 you can obtain, and you can say that this is nothing but a straight line which passes through your point A and B. So here geodesics on a plane are nothing but straight lines. So this is something kind of we know from long back, but here is the mathematical proof for the fact which we already know. So let us move to next example, which is a little bit non-trivial kind of thing. And so example is that find the geodesics on a right circular cylinder of radius r. So it means that just let me use here. So here we have a right circular cylinder, and we have take just 2 point P and Q here on the cylinder, and we want to we can connect this P and Q by some curve which are lying on this surface only. So there are several possible curve here, and we want to find out, say, the curve which minimizes the distance between P and Q, which we are traveling only on this cylinder. See, okay. So here we can simply say that how we can find out. So let us take use cylindrical coordinates, and it's rho, phi and z, and here the x coordinate you can write it rho cos phi, and y coordinate is rho sin phi, and z is equal to z. So any point on your cylinder with radius r is given by r cos phi, r sin phi and z. So here your P is given by, you can write it r cos phi, r sin phi and the z here. Now to find out, say, the surface here, let us use this thing that ds square is equal to dx square plus dy square plus dz square. basically it is this, and we want to find out say length between length of the curve of joining P and Q. So here if you simplify this dx square dy square plus dz square, you can write it in terms of say d rho square. Let me write it here, g11 plus g22 d of phi square plus g of 33 dz square, and you can find out gii is equal to say del x by del rho whole square plus del x del y by del rho whole square plus del z by del rho whole square. Similarly, you can write it g22 as del x by del phi whole square plus del y by del phi whole square and del z upon del phi whole square. And with the help of this, you can easily find out say ds square. So your this thing is coming out. So for right circular cylinder of radius r, your ds square is coming out, ds square is equal to dx square plus dy square plus dz square, and here if x is given as rho cos phi, y is equal to rho sin phi, z equal to z. So using the formula which we have listed here, you can find out say g11, g22 and g33, and in this case your g11 is coming out to be del x by del rho, del y by del rho and del z by del rho. So del x by del rho is coming out to be cos phi, and del y by del rho is equal to sin phi, and del z by del rho is simply 0. So in this case your g11 is coming out to be this cos square phi plus sin square phi, that is equal to 1. So g11 is coming out to be 1 here. Similarly, you can find out g22 as del x by del phi, which is minus rho sin phi, and del y upon del phi is your rho cos phi, and del z by del phi is nothing but 0. So when you find out g22, it is the square of del x by del phi, which is nothing but rho square sin square phi plus del y by del phi square, that is rho square cos square phi. When you add these two, it is coming out to be rho square. So your g11 is coming out to be rho square. So similarly, you can find out as g33. So you can say that your ds square is given as d rho square plus rho d phi square plus dz square. Now for this, your rho is fixed, so rho is given as r. So you can say that the arc element on a right circular cylinder of radius r is reduced to only r square d phi square plus dz square, because the component along this is simply 0, because rho is a fixed quantity. So ds square is given as r square d phi square plus dz whole square. So ds you can write it as under root r square plus dz by d phi whole square d of phi. So here we are assuming that z is a function of phi, and it is simplified as your functional arc length is given by s equal to phi 1 to phi 2 under root r square plus z dash square d of phi. Now if you look at this is nothing but a function on phi and z dash, and here this is independent of say phi and z. So Euler's equation, you can take the help of Euler's equation, and we can say that the geodesics for a given cylinder is the curve for which S is minimum, and you can say that Euler's equation reduces to del f by del z dash is equal to constant, and f is given by under root r square plus z dash square. So when you plug in this value, you will have z dash upon under root r square plus z dash square equal to c. Now you can simplify this. So here we have z dash upon r square plus z dash square equal to some constant c. So you can square it and you can solve it. So after squaring it, you have z dash square equal to c square r square plus z dash square. So you can simplify this. So z dash square is coming out to be c square r square upon 1 minus c square. So here c is constant, r is constant. So here this whole quantity is constant. So you can write it z dash is equal to some other constant, call it say z1. So when you solve this, then it is coming out to be z is equal to c1 phi plus c2. Please remember this z dash here is nothing but double z by double phi. Okay, so when you integrate this z dash as c1, you will get z equal to c1 phi plus c2. Now again this c1 and c2 you can obtain with the help of the initial values, that p and q are the initial values. Is it okay? So now if you look at carefully, then what is this? So here if you vary your phi, then of course your heights will also change, and it is coming out to be that the path which minimizes the distance between any two point P and Q is nothing but helix on the right circular cone. So here in this case, the geodesics on a right circular cylinder of radius r is nothing but circular helix, which is represented by z equal to c1 phi plus c2, where c1 and c2 is may be obtained by the initial condition that here is the initial condition that z of phi 1 is equal to z1 and z of phi 2 is equal to z2. Okay, so moving on, say next example. So here we want to see that geodesics on a sphere of radius c, and we want to show that it is nothing but great circle of this sphere. So here to solve this problem we use the spherical coordinate system, and that is r theta phi. So here in terms of r theta phi, you can write down your x coordinate as r sin theta cos phi, y as r sin theta sin phi, and z equal to r cos theta. So here theta is the angle made by the radius vector with the z axis, and phi is the angle of the projection of radius vector and the angle from the x axis. Okay, so here r is equal to c. So similarly as we have done in the previous case, your arc element on this sphere is given by ds square as dx square plus dy square plus dz square, and that you can find out as g11 dr square plus g22 d theta square plus g33 d phi square, and you can easily calculate g11, g22 and g33. Formula is already given in a previous example. So but let us take very simple one, g11. So g11 is what? Dever x by dever r whole square plus dever y by dever r whole square plus dever z by dever r whole square. Let me do it here. So here you can write it here, your x is equal to r cos r sin theta cos of phi and y equal to r sin theta sin phi and z equal to r cos of theta, right. So here you can find out g11 here. So g11 is dever x by dever r, so that is sin theta and cos phi, and dever y by dever r is equal to sin theta and sin phi, and dever z by dever r is basically your cos of theta. So when you find out g11 is basically square of these three conditions. So when you square these two, you will get sin square theta. So sin square theta cos square phi, cos square, let us so cos square phi plus sin square theta and sin square phi and plus cos square theta. So here when you take sin square theta common, then this is nothing but cos square phi plus sin square phi, that is 1, and ultimately you will get sin square theta plus cos square theta, that is 1. So here in this case you can get your g11, and similarly you can find out g22 and g33. So here g22 is nothing but with respect to theta you are finding. So your g22 is coming out to be dever x by dever theta whole square plus dever y by dever theta whole square plus dever z by dever theta whole square. So you can find out the value of G22 and similarly G33. So you can say that here we have calculated and it is coming out to be that ds square is equal to dr square plus r d theta whole square plus r sin theta d phi whole square. Now here as we have taken that radius is constant and it is given as c, so this dr is coming out to be 0, and so ds square is you can write it c square d theta square plus c square sin square theta d phi square. So this is the arc element on the sphere of radius c, and you can simplify and you can form the functional which gives the arc length between two given point a and b, and you can say that s is given as c theta 1 to theta 2 under 1 plus sin square theta d phi by d theta whole square d theta. So the geodesics on the sphere r equal to c is the curve for which this functional s is minimum. So here your f is nothing but c under root 1 plus sin square theta phi dash square. So let me write it here. Your f is your c under root 1 plus sin square theta and sin square theta and phi dash square. So phi dash square. So here you can say that f is a function of say your theta and phi dash. So here now this is independent of your phi. So here your Euler equation for this integrand is basically what? Del f by del phi minus d by d theta and f of phi dash equal to 0. Now since this integrand is independent of phi, so this term is simply 0, and you can simply write this as f of phi dash is equal to constant. So here we are using this, and you can say that Euler equation reduces to del f by del phi dash is equal to constant. So f is given, you can find out say value of del f by del phi dash, which is coming out to be c sin square theta phi dash divided by 1 plus sin square theta phi dash square equal to constant. Now let us take this constant as some a, and you can simplify this. So when you this is constant divided by c is your a. So when you simplify this, you can square it and simplify for phi dash square. So phi dash square is coming out to be a square upon sin square theta and sin square theta minus a square. So that is this. So d phi by theta is given by a under root a divided by sin theta under root sin square theta minus a square, and which is further simplified as a cosec square theta divided by 1 minus a square cosec square theta. So now you integrate this. So d phi by 1 and this a cosec square theta upon 1 minus a square cosec square theta d theta. So when you integrate, you will get phi equal to integrand of this. Now to find out simplifying this, what you can do, you can write it cosec square theta as 1 plus cot square theta, and you can write it, and this is this simple integral, and here you can take a cot theta as some variable, and you can simplify this integral as minus sin inverse a cot theta upon under root 1 minus a square and plus a dash, where a dash is integration constant. So here when you simplify this, so phi is equal to minus sin inverse a cot theta upon under root 1 minus a square plus a dash. So you take a dash here and take the sign on both the sides, you will get a cot theta equal to under root 1 minus a square. Let me write it here, this is quite clumsy here. So let me write it here, this is your phi here equal to minus sin inverse a cot theta upon under root 1 minus a square, and here we have a dash. So you can write it here that it is sine of, you can take this as you take minus here, and sine of a dash minus phi is equal to a, this is cot theta, this is cot theta, you can take this as a cot theta is under root 1 minus a square. So here you can simplify this, and you can multiply by 1 minus a square here also, 1 minus a square sine of a dash minus phi equal to a cot of theta. So here when you simplify using the formula sine of a minus b, you can write it here, you can take a also. So here you can write it cot of theta is equal to, you can write it some constant of sine of phi plus b of cos of phi. In fact, this is what, this you can simplify as a cot theta is equal to under root 1 minus a square u, and you can write it here sine of a dash cos of phi minus cos of a dash cos of a dash sine of phi, right. So here you can simply say that you can divide it by a also, and you can write it here a, and this, so here you cot theta, and you can call this as your a. So a is nothing but under root 1 minus a square divided by a, and your sine of a dash. Similarly, your b is nothing but under root 1 minus a square upon a into cos of a dash. Is that okay? So your b is given by this. So by taking a and b are these constant, you can write it cot of theta equal to cot of theta is equal to a sin phi plus b cos phi, and if you simplify, you can take cos of theta is equal to this a sin phi sin theta plus b cos theta sin of theta, and this is what, this is cos of phi, this is cos of phi. So this is cos of phi, and if you multiply both sides c, then this is what, this is your z here, and this is your y here, and this is your x here. There is something wrong here, yeah, this is x, right. So here we can say that it is z equal to ay plus b of x. Here I have to look at here, the coefficient of sin phi is a, and if you look at, this is interchanged, so your a is this and b is this, so that you can simplify. So it is just a constant, a is given by minus under root 1 minus a square upon a cos of a dash, but anyway you can always write it cot of theta equal to a sin phi plus b cos phi, where a and b are suitable constant, and when you simplify, your equation is coming out to be some z equal to ay plus b of x. So here in calculation, if I look at here, cot of theta is equal to a cos phi plus b sin phi, and when you multiply by c, it is coming out to be ac sin theta cos phi plus bc sin theta sin phi, and which is nothing but a plane passing through the origin 0 0 0, right. So we can say that the curve which minimizes the extreme, minimizes the functional, is basically a plane through the center of the sphere, and which cut the sphere along a great circle. So here we can say that the required geodesics are the arcs of the great circles. So here we stop here, but before stopping here, you can one point on this example, you can simplify this, and whether it is z equal to ax plus by, or it is given as ay plus bx, but anyway it is a plane passing through the sphere. So here we stop, and we'll meet in a next lecture, where we can discuss the extremal, or say Euler equation for in place of curve, it is the Euler equation for the sphere. Okay, so here we stop, and we'll meet in a next lecture. Thank you for listening us. Thank you.